Hi everyone. In this video we are going to go over two radical mechanisms. The first one is radical addition of HBr, and then the second one is dissolving metal reduction. So these are reactions that we've already learned about, but I told you that you didn't need to know the mechanism just yet because it involved radicals. Well, now we are going to go over those mechanisms. So first of all, let's talk about addition of HBr. So we're going to review. So remember, when we talked about addition of HBr, we said that if you just add HBr, you'll end up with the bromine adding to the more substituted carbon. And then hydrogen will add to the less substituted carbon. And here I'll highlight the double bond there, okay? And then that's Markovnikov addition. Now, if we want the bromine to add to the less substituted carbon on the double bond, remember we add peroxides. So again, if you see a peroxide, like hydrogen peroxide, then just know that that's going to give you anti-Markovnikov addition. Okay, now the anti-Markovnikov addition of HBr does involve radicals. So let's look at the radical mechanism. All right, so we're going to start with an initiation step, like always with radical reactions. And what happens is the peroxide is going to homolytically cleave between the two oxygens. So we're going to form two radicals. And we're going to use heat or light to do this. Now, the reason that this occurs so easily is the bond between those two oxygens is really weak. Now, in the next step, we're going to add HBr. And one of the OR radicals is going to grab onto a hydrogen. Or it's going to abstract a hydrogen. And then an electron will be left behind on bromine. All right, so we've generated a bromine radical, and now we can go on to the propagation steps. So in our propagation step, we'll draw our starting material, so our alkene, and then we're going to show bromine forming a bond with the alkene carbon. So what happens here is, again, the pi bond is going to homolytically cleave, and one of the electrons will be left behind on the more substituted carbon because we want to form the more stable radical. The other electron is going to make a bond with bromine, so they're going to form a covalent bond. Okay, so now we have a radical. And again, remember, this is a tertiary radical. And so this is going to be more stable. So for instance, if we had tried to make a bond with bromine and the tertiary carbon, then we would have had a single electron on the very end of the molecule. So it would have looked like this, and that's a primary radical, which is not as stable. And we are going to go through the more stable intermediate. So that's why bromine adds to the less substituted carbon. So this might also help you kind of remember the anti-Markovnikov addition reaction, because now we're going to see the mechanism unfold here. All right, so now in the next step, we're going to add more HBr, and we're going to abstract a hydrogen from HBr. So our tertiary radical electron will form a bond with hydrogen, and we're going to leave an electron behind on bromine. All right, so now we have our final product that we wanted to form, and then we've regenerated our bromine radical. And then in the termination step, again, I'm a lazy chemist, so I'm going to couple two bromine radicals. There we go. All right, so really the important steps here are the initiation step, where we form our bromine radical, and then the propagation step, where the bromine adds to the less substituted carbon. So let's actually make a note of that. Oops, adds to less substituted carbon. All right, so if you were kind of wondering why peroxides make a difference for hydrohalogenation, now you know why. It's because we want to form the more stable intermediate radical. Now let's also look at dissolving metal reduction. So we talked about this in our alkynes chapter. So recall that if you have an alkyne and you add sodium and ammonia, well, liquid ammonia, you end up forming the transalkene. So the R groups are on opposite sides of the double bond. Now, I told you that this was a radical mechanism, so you didn't have to worry about it at the time, but now let's go over that radical mechanism. All right, so the first thing that happens is sodium has one valence electron that it can donate. So it is going to donate its electron to carbon. And as a result, one of the pi bonds is going to move to the other carbon, and both electrons are going to move. So just note, two electrons move over from the triple bond, and then sodium will donate its one electron to carbon. Okay, so let's draw the resulting radical. All right, so we have a lone pair on the carbon on the left, so now that is negatively charged. And then we just have a single electron on the other carbon on the right. So this is a radical anion because it's negatively charged. And this is actually a very strong base. Now, the reason we end up forming this trans configuration is due to those electrons. Because remember, according to Vesper theory, electrons want to be as far apart as possible. So this forms the trans configuration. Because electron groups, want to be far apart. Okay, so now let's add in the ammonia, NH3. And what ends up happening is the lone pair of electrons is going to grab a hydrogen, and then electrons will be left behind on nitrogen. So we're going to form the following radical. And then in the next step, another sodium atom will come in and donate its electron to the radical carbon. So we're going to form a pair of electrons on the other carbon. Okay, so now we have an anion. And in the next step, we're going to add more NH3, and that lone pair of electrons can now grab a hydrogen from ammonia, and we get our final product. All right, so kind of an interesting mechanism, right? Sodium has that electron it can donate, so that moves electrons over to the other carbon. That lone pair of electrons is then going to grab onto a hydrogen, and then sodium donates another electron so that we have another lone pair that can grab onto another hydrogen. So really the main reason we form a trans alkene here is due to the fact that those electron groups want to be as far apart from each other as possible. Okay, so I think we'll stop here for today. Next time we're going to talk about some interesting radical mechanisms that occur in our atmosphere. So we'll talk about ozone, as well as molecules called CFCs. So you might have heard of them before, but we'll talk more about them in the next video. So I will see you then.